In this video, I want to talk about factoring finite state machines. So factoring finite state machine is a very useful technique when you want to break complex finite state machines into a smaller interacting finite state machines. So let's just take a look at one example. Let's just consider the traffic light example that we had before, and let's just say we want to have a parade mode. So if we are in a parade mode, the system should behave differently than if it's in a regular mode. So based on this, we have two additional inputs. P is for the parade mode and R is for the regular mode. So when P is 1, or when we are in the parade mode, the Bravado Boulevard light stays green all the time. So we basically don't change the state, don't turn the traffic light on the other street green. But when R is 1, we leave the parade mode and the system behaves the same as before. So you might say, why do we need to have two inputs to show this parade mode or the regular mode? We can do it using only one input too. So what if we only use one input, P? If P was 1, that was representing the parade mode, and if P was 0, that was representing the regular mode. But the whole point is that for you to see, even with these minor things, if you don't factor your FSMs, the system becomes more and more complex. So in the unfactored FSM, if you identify the sets of inputs, again you have P, R, P representing the parade mode, R representing the regular mode. We have TA and TB, the traffic sensors. Also we have the clock, and also we have this reset, which we didn't show here. And then based on that, we have LA and LB, basically the traffic light on the first street and the second street. As for the factored FSM, what we can do is that we can basically create two smaller FSMs. One showing whether we are in the parade mode and the regular mode. And this small FSM provides a single input that we can feed to the regular FSM that we had before. So we need to make some modifications, but these modifications are much simpler as if we use the unfactored FSM. So you might ask how much simpler the factored FSM is in comparison to the unfactored FSM. So let's just take a look at the state transition diagram of the unfactored FSM. As you can see, things are exponentially more complex. We have both the parade mode, the regular mode, and for each one of them we need to consider whether P or R are 0 or 1, right? So as you can see, even for such a small tweak in our system, things become more and more complex. But if we follow the factored FSM approach, then we have one FSM only helping us to choose the mode for the FSM, and the other one is for choosing the traffic light, right? Of course, as you can see, we have to make some modifications based on the output of this FSM, but nonetheless, implementing and understanding this system is much easier than the unfactored FSM. Of course, we don't go over the different techniques that we can use for factoring FSMs, but this was just for you to have a better idea how the more complex systems work in general, right? So not every finite state machine contains only one single finite state machine. There might be multiple finite state machines that can be combined to create a larger one. And we have more and more examples of finite state machines too. So this one is an example of a phone answering machine. Of course, the symbols that we are using here are a bit different. So we have basically whenever someone calls, you wait 4 seconds. If the person on the other side lifts off the phone, you start talking. After the talk ended, basically you return the call, or like you go back to the initial state, right? Or if 4 seconds pass and nobody picked up, then some text is being played, you hear a beep, and then you have 8 seconds of recording, for example, here, and then after that you go silent, and then one more beep, and then the system goes back to the initial state when nobody was talking. So this is a very basic example of finite state machine that is being used in answering machine. Another example that I can show you is, if you ever played a video game, you should know that all the video games have finite state machines inside of them. Of course, these can be more and more complex. They definitely use factored finite state machine, but they have finite state machine nonetheless. So for example, your character can be in the sleeping state. If the fatigue is low, they became awake. Based on that, if they're hungry, they start searching for the food. Whether they find the food or they don't find the food, some other things happen. If they are like hunting, or if they are like fleeing or recovering, and all these things, as you can see, these are the different states that your character can be in. And then depending on the type of the input that you might have to your system or for the character, you choose a different path. So if you are less tired, you awake. If you get more tired while you are awake, you go to sleep. Or if you're hunting and you spot a predator, you flee, right? But let's say if you are in the recovery mode, right? And then recovery is over, you become awake, but if you are still tired, you go to sleep. As you can see, this is something that you can think of as an interconnected mesh of states, which can be more and more complex, but using the concept that I covered in the past few videos, you should be able to design a small finite state machine, and you should be able to combine several of these finite state machines to come up with more complex finite state machines. So I highly suggest you look for these examples in your video games that you play, or in other things that you might encounter.